And here we are at the physics video lecture, fluid mechanics video lecture 3. So let's see where we were. We're going to go ahead and write down the Euler equation and the divergence equation. So the Euler equation, which we know is just Newton's law, looks like this: dv dt v dot gradient onto v is equal to minus 1 over rho gradient of the pressure. That's 3 equations, and our 4th equation is the divergence of v equals 0. This one here came from the continuity equation, and this came from Newton's law. So what we had been doing, and let's go ahead and add the external field in there. The last thing we had done was hydrostatics. So last time, hydrostatics, the entire left side of the equation here vanishes, and we're just dealing with the right side right here. So last time, hydrostatics, there we have gradient P is equal to rho times G, the vector, and we got some good results out of this. First thing we had was the pressure depth formula, P equals P naught minus rho gz, where P naught is the pressure up at the z equals 0 level. Then, based on that formula, we had Archimedes' principle. And a couple of applications, but the buoyancy force is equal to the weight of the displaced fluid. So the density there is the fluid density that you're in. So we did a couple examples of that. And finally, we had the pressure in a gravitating fluid that I left for you guys to finish up. So gravitating fluid sphere, we assumed the sphericity of it. So I gave you guys a few things to tackle to complete that problem. And the nice thing about this problem here, it's a little more advanced, and we find this as a limiting case at the very surface of the sphere. So I'll just draw a little sphere here to complete the discussion. So you've got that sphere there of radius r, and it's gravitating incompressible fluid, but at the very surface there, you're going to find that it satisfies the pressure depth formula, which is linear. Of course, it's not going to be linear all the way into the center. You're going to see it's quadratic dependence, but the derivative is constant, so you got that linear dependence there. So far so good. That's the fluid statics, hydrostatics, and now we're going to move on to fluids in motion. So for fluids in motion, we need the entire, we need more of the Euler equation. So now fluids in motion. Really, the best thing to start off with is the rotating bucket, which actually has played a big role in physics. Newton considered the rotating bucket, wondering about centrifugal forces and centripetal forces. But for us, the rotating bucket will introduce a bunch of interesting stuff. So the idea here is that we have an X, Y, and Z axis, and we have a bucket of fluid that's rotating, and it's rotated long enough so that the entire mass of the fluid in there, let's just call it water, is rotating along with the bucket. Okay. So we'll just call it the rotating bucket. And so V is going to be not constant, but time independent. Rotating bucket. So after, just write dV dt is equal to 0. So it's a steady state. And I'll say a little bit about this before I write down the solution. We can get the solution very easily. This is an example where we plug the solution that we just infer into this equation and learn something else, or some interesting stuff. It's interesting though that we wouldn't be able to get this solution from starting at t equals 0. We would not be able to have a bucket of water and then just start up the rotation and wait for a long time and then have the equations deliver the transient, the result of that rotation, where it would spin up and eventually it would just be rotating as a solid unit. So that is actually not possible with this equation, because we would lack that proper frictional component that actually exists, and that's what helps spin the thing up. Nonetheless, we're going to have the following. Since it's going to end up rotating as a solid, as a unit, we'll take that as the following. So the velocity field is just going to be omega cross r, and so we've got an omega vector here. Let's go ahead and use another color. So we have a vector omega, and this vector r we're going to take only in terms of the x and y coordinate. So here's what we're looking at. Velocity is omega cross r, where omega is equal to 0, 0, omega along the z-axis. And we're going to just take r as being x, y, 0. So we're assuming that throughout the bulk of this, it's got the same, it has no z velocity component. We could have x, y, z here and not get anything different in terms of the velocity. But for further applications, we want to just have this r magnitude be the x squared plus y squared, root of the x squared plus y squared. So that's why we're doing this. And now we have to calculate the omega cross r. And so that cross product is just going to have x and y component. And it's really the same type of thing you have from uniform circular motion. So we're looking at minus omega y omega x 0. Okay, that's our velocity vector. And now, of an object rotating as a unit, as a solid. And now we have to go into this equation here, and we've already gotten rid of the time dependence, so we have to inspect what happens with this nonlinear term. Okay, so yeah. Okay, I'll go ahead and put this up here again. dV dt v dot grad v plus g. And we saw this one, we can already strike. This here has x, y, and z components, and so we'll write those out. We're going to have vx d over dx plus vy d over dy applied to vx equals minus 1 over rho dp dx. G is of course pointing down, right? Got the z-axis pointing up there. So G is pointing down, got nothing there. Second one the same. Vx d over dx applied to v sub y is equal to minus 1 over rho dp dy. And then for the z component, we're going to have no v, we have no v sub z here. So we have a 0 on this side, and we have minus 1 over rho dp dz minus g, because that's how we're orienting. Okay, so now what do we have here? Vx d over dx of Vx, okay. D over dx of Vx, of course, is 0. And we have Vy d over dy of Vx. So on this equation, we have the V sub y, which is omega x d over dy Vx, which is minus omega. Equals minus 1 over rho dp dx. And this next equation, the Vy d over dy is going to deliver a 0. So we have Vx d over dx. So V sub x is minus omega times y. D over dx, V sub y is going to give us another omega again. Minus 1 over rho dy. And finally we have 0 is equal to dp dz minus g. Actually minus right here. Good. Okay, so this is going to be minus signs cancel, omega squared x. So we have rho omega squared x is the derivative, so we're going to have rho omega squared x squared over 2. Here we're going to have the same thing in y. Okay. So here's what we can get for the pressure. It's going to be P0 plus rho over 2 omega squared x squared plus y squared. And then here, dp dz is going to be minus g, so we'll have minus gz. And that's our pressure distribution. Let's consult here for a moment just to make sure. Yep, there we go. Omega squared over 2 minus rho dz equals constant. So good, let's put a box around here. That's the pressure distribution, x, y, and z of that rotating bucket. And what we're going to do is say at the surface, we have atmospheric pressure. Okay. So at the surface, we have atmospheric pressure. Therefore, at the surface, these two terms vanish. And what we see is that we can get z as a function of x and y. So at the surface, put a note right here. At the surface, Z0, just say that's the atmospheric pressure. And here's what we get. Z is equal, so it's going to be 0. So Z is going to be equal to 1/2 or 1/2G, or how about we write rho omega squared over 2G x squared plus y squared. So that defines the shape of the surface, and that is apparently a paraboloid. Hold on. Here's an extra factor of rho. So we'll catch that mistake. We can have minus rho G, and then that rho is eliminated from this answer. That's better. Doesn't depend on the density. Good, so there's the shape, and I'll just write a note or two right under here. Surface Z of x and y, and yeah, so if you're to draw this again, and you've got your axes, then the fluid has this paraboloid shape. So it dips in, it's kind of a dish, and that depends on the rotation speed. Okay, we got to put a 1 right there. Okay, 1/2 rho squared. Yeah, now we're good. That's omega squared over 2G. So yeah, by controlling omega, you can control the depth of this paraboloid, and therefore, if you want to use that to make a reflecting mirror, you can control the focal length. Because the thing about the paraboloid is that all parallel incoming rays are reflected to a focal point. Okay. Now what we have to do next is discuss this a bit more. Yeah. So what I want to do is consider the kind of vector analysis aspects of this whole situation here. So look, and that'll motivate a longer or shorter section on the vector analysis. But let's just write here vector analysis. Kind of discuss what we've had so far. We have this velocity equals omega cross r, and again we're doing two-dimensional, x and y. Ignore the z component. In our description of r, it's like a cylindrical type of r. Okay. And what we want to do is calculate the curl of this. So we could write this as follows: I, J, K, 0, 0, omega, x, y, 0, using the determinant rule. And then we see we're only going to get one of these components for the curl. It'll be the kth one. Not a cross product. derivative. That's what's going on here. Once more, ijk d over dx dy d over dz. And we'll go ahead and put the v in, which was minus omega y omega x 0. Okay, so good. The curl of this I hat, we've got a 0 and a 0. J hat, we've got a 0 and a 0. So it's just the k hat, and we have d dx omega x minus d dy negative omega y. So we just get 2 omega k hat. So that's the curl. And you can see this is just like a rotational quantity. The curl of that vector field, I, J, K, for this circulating quantity like this, is like a rotational quantity pointing up in the k hat direction. And let me say something about the top view of our bucket. So we're looking down on the bucket, and there's our x and y axis. Okay. We've got that kind of rotation. And the curl measures how much a little paddle wheel that you put in here would actually rotate along with the fluid. In this case, because it would have a higher velocity here than down there, there's going to be it's actually going to rotate that little paddle. In fact, the expression curl in other languages is just referred to as the rotation. Okay? So this is a place to, to get some intuition on some of these quantities of vector analysis. The other thing we can look at is the integral theorem of Stokes. So, integral theorem, and we have the curl of a vector dotted into a surface normal, okay, and I'll just say area here, that's equal to the line integral around the boundary of that area with all the appropriate orientations of f dot dl. So let's go ahead and evaluate this integral for this scenario that we have here. So let's see. The curl of f we just had here, so we'll go directly underneath here. Curl of f is 2 omega k hat. We're going to dot that into n hat, which for this object is just the k hat vector itself. Okay, n hat, we're looking on, that was the top view, but again, we're looking in the bucket. So that's k hat, and that's n hat because we're talking about the surface. Good, so k hat dotted into k hat, d area. Now what about our vector here? Omega, barely recognize that's an omega cross r. Well, we know for that omega cross r, in terms of its direction, it's always tangent, okay, like that. So it's always tangent, and since we're going to go around the circle, we're just going to pick up, in fact, I can just say we're going to pick up an omega and then an omega r. And since we're going around here, let's make sure we define this right. So this area is the circle pi r squared, right? It's the circle of radius capital R. So then we're going to have the omega r, and then we're going to have 2 pi r for going around that circle. Okay. So this here was 2 omega pi r squared. And over here we have omega r to pi r, and that's equal. Omega pi r squared. So yeah, it's a test or an example of Stokes' integral theorem. Okay, good. So the next example gets even more interesting. Yeah. The next example consider V equals omega cross r as before divided by r to the n. Or we can multiply it by r to the n, which is opposite power of this. And again, we're taking r is equal to root x squared plus y squared. Okay, we're not worrying about the z component here. What you can show is here the curl of V is equal to 0 when n is equal to 2. That's actually a special case of this thing. Curl of V is equal to 0 when n is equal to 2. So what you can do is take this here. Okay, so we've got the V equals omega cross r over r squared. And you can see what that is the same type of circulation, except that because it's divided by r squared, it's getting weaker as 1 over r. So if you were to look at this, then if you're circulating here, you've got ever smaller magnitudes as you go out there. And you might think that's kind of contrived, but it actually plays a big role. I'll give it a physical interpretation in a moment. Okay, so this here, let's just call this homework. So the thing to do is to write out this V here and then do the curl. So in fact, we're looking at the curl of, and the numerator is the same as before, so minus omega y over r squared, omega x over r squared, and 0. Okay. And because that r squared is equal to x squared plus y squared, you got to take a little care doing your chain rules and what have you, but you can just stay in the Cartesian coordinates. You'll find that this curl vanishes for n equals 2. And then we want to go back into Stokes' equation, Stokes' integral theorem. So this time, we're going to, I'll write the whole thing out again. So we're going to have curl of v dot n hat dA is equal to v dot dl, boundary of A. Well, here's the thing. If curl of v equals 0 when n equals 2, we're getting a 0 here. But on the right side, you can actually see what we're going to have here. Because, again, v and dl are parallel when we're going around the circle. So we can easily just write down the magnitude of v, which is omega over r. The magnitude is going to be omega over r. And again, we're on the circle of radius r times 2 pi r equals 2 pi omega. Okay, so what's going on here? How did we get a 0 there? Did Stokes's integral theorem break down? It did not, because this curl vanishing for n equals 2 is true everywhere except for r equals 0. So curl of v equals 0. Here we'll do it this way. 0, r not equal to 0, undefined when r is equal to 0. So in fact, what you have is the curl of this vector field with n equals 2, this one right here, is a sort of delta function. It's a sort of a delta function. And this vortex that we're looking at here has a very interesting physical interpretation and plays a huge role in this theory. I'm going to consult the clock here for a moment. Okay, good, perfect. Yeah, so put some note about what we just discovered here. And the reason is that this curl v is undefined when r is equal to 0. Right, when r is equal to 0, you got something going on here. So this thing actually acts as a delta function. And let's look at the physical interpretation of this vortex. Okay, so vector field B is equal to omega cross r squared, and more explicitly, this one right here is equal to minus omega y omega x over r squared 0. Okay. R has to be x squared plus y squared, okay? Here's what we do. What about the magnitude of this thing? If we just multiply through by r, we have r, in fact, I'll just write magnitude-wise. So, magnitude. We know the direction of this, it's just tangent as it's circular motion. So the magnitude v times r, or r times v, is equal to the magnitude of omega cross R over R. I just cross multiplied one of these powers of R over the other side. Yeah, but the magnitude of this thing here, this is just a unit vector, directions are clear, so that is just equal to omega. So yeah, if we have R times V is equal to omega is equal to constant, what does that remind us of in the context of circular motion? Reminds us of the conservation of angular momentum, right? You could just put an M in front of here, you'd have angular momentum, or you put a density, you'd have angular momentum per unit volume, okay? And since we're working with constant density, it's fine the way it is. So compare this to conservation of angular momentum. And this is something everybody has actually seen, namely, say in a big bathtub, when it drains and you actually get that vortex that just tapers down to a little filament, then we're actually talking about this phenomenon here. You've got a big tub of water with very little angular momentum in it, and nonetheless, when it circles the drain, it circles and gets a tighter and more rapid circulation. So, angular momentum, and let's just call it the bathtub vortex, the circling the drain vortex, okay? And in this ideal form, right, it's tapering all the way down to a little singularity. And that singularity, right, that can be represented with the delta function, actually plays a role explicitly in superfluid hydrodynamics. Maybe I'll get to. We have to talk about potential flows and stuff first. So yeah, this is a great example to open your eyes to some of these fluid phenomena and the connection to the formalism. Okay, so yeah, make it, take this and make it more logic. The logic's here, but spread it out in your notes, put some words in between, and you should have a good development. Okay, so this was also in order to motivate, and I'll just write here next. We have to do a bit of a review of vector analysis. So note next. Vector analysis review. Because there are going to be things that come up. It's kind of like the beginning of your electricity and magnetism course, where you spend a whole week doing vector analysis. We won't spend a whole week on it, but we're going to at least review the essentials. And we also have to do a little bit of thermodynamic relations that we'll also take a look at. So that's what we'll do next time. We'll do at least write down a big vector analysis review, and then we decide how much of it we want to actually prove. Ideally we prove everything that we do in the semester, but who's to say? That's what's coming next, vector analysis and thermodynamics, and then we'll go back into the Euler equation. Okay, good. See you guys next time.